Hey everyone, welcome to another Deep Dive Explainer. Today, we're unpacking a fascinating new solution to a really frustrating accuracy bottleneck in AI video analysis. You know, if you build multi-agent systems or work with frontier vision models, you've probably hit it, that strict performance limit where you just hit an accuracy ceiling. Well, there's a brand new archive paper out by researcher Durga Sandeep Saluru, and it introduces this brilliant pure inference-time routing method that literally shatters the ceiling. It's a real game changer. So let's get right into the engineering. Okay, let's dive into this with a clear roadmap for our engineering deep dive today. We'll cover the video QA accuracy ceiling, the problem with majority voting, how cross-model routing actually works, the benchmark results, and finally, exactly how to implement this in your own stack. Section 1, the video QA accuracy ceiling and the massive hurdle currently facing state-of-the-art video models. As developers, we generally rely heavily on consensus, right? I mean, if we ask a model a question 3 times and get the exact same answer 3 times, we typically trust it. But here is the catch. What happens when frontier AI models confidently agree on the exact wrong answer? Because despite our absolute best efforts, state-of-the-art video LLMs are hitting a strict performance limit when faced with highly complex, inferential tasks. It's a huge problem. To really see this, we need to look at the CVPR 2026 challenge benchmark, known as Implicit QA. Now, why is this specific challenge so incredibly difficult? Well, because the correct answer is never, ever explicitly shown in the video frames. The model can't just hunt for a pixel that gives the answer away. Instead, it has to reason deeply about off-screen events, it has to figure out line-of-sight cues, understand causal structures, and literally map out spatial layouts across entirely different camera shots. On this benchmark, even the absolute best video LLMs are gasping for air right at the edge of their accuracy limits. Moving to Section 2, the problem with majority voting and how it actually amplifies our blind spots. So, conventional self-consistency strategies usually rely on majority voting across repeated samples from the same model. It's a standard best practice. But here's the crazy part. On the implicit QA benchmark, this strategy actually makes performance worse. Think of it like this. It's basically like 3 people studying for an exam using the exact same flawed textbook. If they all misinterpret a causal link, they're all going to confidently deliver the exact same wrong answer. Because their errors on these hard questions are highly correlated, majority voting doesn't fix the mistake. It literally just amplifies that shared blind spot. You can really see the stark contrast here between the old paradigm and the new approach. In traditional self-consistency, the variance you see in the output is, well, it's essentially just stochastic token sampling. It's random noise. It's not independent reasoning. But disagreement-based routing turns that whole idea on its head. Instead of forcing a flawed consensus, it actively looks for variance and uses it as a signal to route the query to a completely secondary model. It breaks those correlated errors right in their tracks. All right, Section 3, disagreement-based cross-model routing, and the aha moment of the research. Let's move to and see how this builds into an incredibly elegant 4-step inference pipeline. First, you triple sample a primary native video model. In this paper, they used Gemini 3.1 Pro Preview with the temperature strictly set to 0. Second, you compare the outputs. If all 3 match, boom, you return the answer. Third, you flag the instances where the samples disagree, which turns out to be about 20% of the dataset. And finally, step 4, you route only that ambiguous 20% to a second model from a totally different family, Claude Opus 4.8, which steps in using an adaptive thinking strategy. When you break down the queries, the sheer efficiency of this routing split is just beautiful. 80% of your queries handle standard consensus with instant output from the primary model. Only the tricky 20% get routed out to the secondary model. And what makes this so powerful is that this is a pure inference-time procedure. I mean, there is no new training data, no fine-tuning, 0 human-labeled annotations. You're just cleverly managing API routing logic to capitalize on genuine sample-to-sample disagreement. Section 4, benchmark results and gains. Let's look at the empirical proof. And this brilliantly illustrates exactly how well this routing method works. On the held-out 172-question CVPR 2026 Implicit QA challenge test set, this pipeline hit an 82.03 overall average accuracy. That is a plus 1.81 performance jump over the absolute best single sample of the primary model alone. I mean, on a benchmark where frontier models are basically hitting a brick wall, a nearly 2-point gain purely from inference-time routing, that is a massive win.
Drilling down into the 1001 question validation set reveals exactly where these gains are hiding. The performance jumps were heavily concentrated. We're talking a massive plus 5.49 in motion and trajectory, plus 3.45 in inferred counting, and plus 1.82 in vertical spatial reasoning. Now, why those specific categories? Well, those are the areas that depend most heavily on cross-shot reference resolution. The secondary model's distinct architecture perfectly resolves those tricky cross-shot references, essentially bypassing the correlation floor that tripped up the primary model.
Finally, Section 5, how to actually implement this with highly actionable engineering takeaways. So the crucial point is how you configure this locally. First, and I cannot stress this enough, your primary model's temperature must be 0. Actually, scratch that, it has to be exactly 0. Higher temperatures introduce random token noise, and that completely obscures the pure disagreement signal we're looking for. Second, use 2 entirely distinct model families so their error modes don't overlap. Third, just expect a slight bump in end-to-end latency, but remember it's only for the 20% of queries that trigger the routing. And fourth, ensure your video preprocessing matches the secondary model's expected uniform frame sampling. This whole paper really proves that sometimes the answer to a bottleneck isn't throwing more training data at the problem, it's just smarter inference architecture. By just listening to a model's internal disagreement, we can dynamically route around its blind spots. So I'm going to leave you with this. How will you apply this elegant disagreement-based routing logic to break the accuracy ceilings in your own multi-agent AI pipelines? Thanks for joining me on this explainer, and as always, keep building.